Hello, my name's Darren Holmes, and today in the book Get Started with MicroPython on the Raspberry Pi Pico, we're going to look at Appendix C, Programmable I/O. So the book says in this appendix we look at code that looks very different to the code we've dealt with in the rest of the book, and that's because we have to deal with things at low level. So most of the time MicroPython can hide a lot of complexities of how things work on a microcontroller. So today we're going to get into a little bit of programming at a very low level. So in the section that says data in and data out, it says throughout this book we've looked at ways of controlling the pins on your Pico using MicroPython. We can switch them on or off, we can take inputs, and even send data using dedicated SPI and I2C controllers. It says, however, what if we want to connect a device that doesn't communicate in SPI or I2C? What if it has its own special protocol? It says on most MicroPython devices you need to do a process called bit banging, where you implement the protocol in MicroPython. It says using this you turn the pins on and off in the right order at the right time to send data. Now there's a few downsides to this. The first is that it's slow. So it says MicroPython does some things really well, but it doesn't run as fast as natively compiled code. It says the second is that we have to juggle this with the rest of our code that is running on the microcontroller. So it's really hard to time things out and get inputs from other devices at the same time. And it says the third is some timing critical code can be hard to implement reliably. So it goes on to say Pico has a solution to this, and it's Programmable I/O. These are some extra, really stripped back processing cores that can run simple programs to control the I/O pins. It says you can't program these cores with MicroPython, and you have to use a special language just for them. But you can program them from MicroPython. And then they go on to show you an example. So before we go any further, I just want to refer you back to the RP2040 datasheet. And looking at the table of contents, Section 3 talks about the Programmable I/O. Section 3.3 is Assembler with PIO Assemb. So Section 3.4 talks about the instruction set. And Section 3.6 has examples of programming the PIO. And you'll notice Section 3.6.2 is on programming the WS2812 LEDs, which we're going to be using in this chapter of the book. So as we're scrolling down to Section 3, I just want to stop for a moment at Figure 2, a system overview of the RP2040 chip. You'll notice we have two processor cores, 0 and 1. These are the two cores that we've been using so far. You'll notice they connect directly to your GPIO pins. So those are your digital I/O pins. These processors also connect over to the peripheral block. And in the peripheral block, we have our SPI, pulse width modulation, and I2C. So these are kind of separate processors. They serve a specific function. So we could be doing things over in core 0 or core 1, running our code. And when we send data out on SPI or I2C, these peripherals take care of processing them. So if we need to convert parallel data to serial data, it's handled here in the peripherals. So what we're going to be working with today is the Programmable I/O. So down here we have two separate Programmable I/Os, and these run independently from our main processor cores. They're also independent from our SPI, pulse width modulation, and I2C peripherals. So these are actually separate processors that we have access to that we can program independently of our main processor cores. So Chapter 3 is all about Programmable I/O, and in Section 3.1 they give us an overview. So you can see here in figure 38, they show us a PIO block level diagram. It says there are 2 PIO blocks, so this is representing one of those blocks. It has 4 state machines each, so they're labeled 0 through 3, and the second PIO block has another 4 state machines. It says the 4 state machines simultaneously execute programs from a shared instruction memory. So you notice down here we have an instruction memory that holds 32 instructions. So we can't hold very many instructions in here, so we can't put large programs in. So I just wanted to show you section 3.3, which is the PIO assembler. So section 3.3.1 talks about directives, and the following directives control the assembly of PIO programs. So if you see some of these, they're not actually Python commands, they're not assembly commands, they're actually directives. So they tell the assembler how to do something. Section 3.3.2 talks about values, so you can have integer, hex, binary, or symbol. Section 3.3.6 talks about instructions. And section 3.4 gives us the instruction set. So you can see here PIO instructions are 16 bits long and have the following encoding. So when you look at table 376, PIO instruction encoding, you can see there's a total of 9 instructions that are available to us. And then underneath, they break down the instruction and what's required to use the instruction. And then finally, in section 3.6.2, they talk about the WS2812 LEDs. And you can see the LEDs are driven by a proprietary pulse width serial format. So I know the RP2040 datasheet can be a bit overwhelming, but I just want to point out a few of those items to you, just so that you know where all this information is coming from. So in the book it says let's take a look at an example. So what I'm going to do is I'm going to type all this code and the code on the next page into Thonny. So you can see in Thonny I have the first section of code. I'm not going to talk about it at the moment. And then I've entered the second section of code, so I'm going to run this and show you what it does on the Raspberry Pi Pico. So using the built-in LED on the Raspberry Pi Pico, we can see that it has 3 brightness levels. So it's bright, dim, and medium. So coming back and looking at our code, you can see we're going to use 3 libraries. RP2 that we haven't used before, machine, and uTime. So we're going to import the entire uTime library, but we're only going to import pin from the machine library. So when we use pin, we don't have to say machine.pin, we can just say pin. I want you to note that pin starts with a capital P. And then from the RP2 library, we're going to be importing the PIO, state machine, and ASM_PIO library functions. So then we have 3 blocks of code, each starting with @ASM_PIO. So this is telling MicroPython that this code is not Python code. It's easier to start with the 3rd block of code, and in the 3rd block of code we're defining a function as LED full brightness. So in here we're going to set pins to 1. So what this does is it turns on the output pin. Please note this is not a capital P. In the first line you can see we're setting a parameter. So we're going to set init equal to PIO.output high. So because this is full brightness, we want the pin to be on all the time, so we're going to start with it on. Now in the second block of code, you can see there's 2 lines in here. One that sets pins to 0 and one that sets pins to 1. So half the time the pin is going to be on. The other half the time, the pin is going to be off. Initially, we want to start this block of code with the pin low. So we've defined this as LED half brightness. Then in the first block of code, we can see we have code that's identical to the second block, except it's followed by a number. So each line of code actually takes one machine cycle to execute. So by putting a number after the line of code, it's going to cause a delay, in this case of 2 machine cycles. The book tells us this number can be anywhere between 1 and 31. So what we're doing here is defining LED quarter brightness, because the first line executes for 3 machine cycles. So for 3 machine cycles, the light will be off, and for 1 machine cycle, the light will be on. And we're going to start this process with the pin in the low position. So the next 3 lines of code are setting up our state machine. So we actually have 8 state machines labeled 0 through 7. So you can see in the book they're using 1, 2, and 3. Each state machine is going to be running a different procedure. So the first one is going to be quarter brightness, the second one is half brightness, and the third one is full brightness. Each one is going to be running at a frequency of 10 kilohertz. You can see in here we're setting the base pin to 25, and you'll have to remember, or look it up in the appendix, that pin 25 is the Raspberry Pi Pico's built-in LED. So looking at our main program loop, you can see we have an infinite loop set up with while true. We're going to activate the first state machine, which is quarter brightness. We're going to wait 1 second, and then we're going to deactivate state machine 1. Then we're going to start up state machine 2, which is half brightness. We're going to wait 1 second, and then we're going to deactivate state machine 2. Then we're going to activate state machine 3, which is full brightness, and after 1 second we're going to deactivate state machine 3, and then we're going to continue through this loop infinitely. Please note that the state machine is running even while our main processor is waiting for 1 second. Okay, so after you've read that section of the book over a few times and got a better handle on it, we can move on to a real example. So in a real example, what we're going to do is talk to some Neopixels. And basically what these are is RGB lighting with a built-in serial communication port on it. So what we're going to do is we're actually going to go through and take a look at what these WS2812Bs or Neopixels are. So this is a close-up of a Neopixel, also going by the part number WS2812. Now if you have the WaveShare MicroPython Programming Learning Kit, the Wave 19693, in it you will have received an 8-bit WS2812 RGB LED strip. You can see that there's actually 8 of these Neopixels soldered onto a small board. Checking over on Abra's website, you can see you can buy these in strips of 10, or you can buy a package of 10, but remember these are surface mount and you would have to solder wires to them individually. So coming over to learn.sparkfun, you can see that we can actually purchase these in fairly large strips. So these would be a package of individual Neopixels that you would need to solder wires to somehow. You can also purchase them individually on breakout boards. You can purchase them in large strips of 1 meter or 5 meters. They also have them mounted onto strips or into rings. And in here they give you the WS2812 hardware overview. It says they're more than meets the eye. So basically these are an RGB LED with a microchip built into them, so we control them over one-wire communication. So you can see here they have a section on data transmission interface, and it says the communication interface between a microcontroller and the WS2812 is weird. It's one wire, but it's not like a standard UART serial interface. So this interface is time specific. So we've seen in other kinds of communications, especially serial communication, we need a clock signal. So in this case we need a clock signal, but somehow on that clock signal we need to send a logic 0 and a logic 1. And we do that by adjusting the pulse width. So it's the duty cycle that actually changes on these. So for logic 0, you can see we have a high time of 0.35 microseconds and a low time of 0.8 microseconds. That gives us a total of 1.15 microseconds, which works out to about 869 kilohertz. For a logic 1, we're high for 0.7 microseconds and low for 0.6 microseconds. So that gives us a total period of 1.3 microseconds, and that works out to 769 kilohertz. So the average clock frequency is somewhere around 819 kilohertz. So you can see here it says the data is sent in a sequence containing 24 of those bits. So 8 bits are for the color, followed by the low reset pulse of at least 50 microseconds. It says here the larger the value of a specific color, the brighter it will be. If the color is set to 0, the LED will be off. If every color is set to its maximum of 255, the LED will be as bright and white as it can be. It says here that microprocessor, like those of the Raspberry Pi, can't give you a reliably timed pulse. Even if one bit is less than a microsecond off, that could mean the difference between purple and maroon. So we're going to be using the Raspberry Pi Pico's Programmable I/O so that we can get exact timing that's required by these NeoPixel LEDs. So you can see in figure C1, they have an example of connecting an LED strip to the Pico. So we're going to wire it up the same way they have it wired up. We have the ground wire. We're going to take the power off the plus 5 volt pin, and we're doing that rather than taking it off of the Pico, because the plus 5 pin comes from your USB port and it can provide you with more current than going through the Pico. So because this runs on 5 volts, we need to be a little bit careful about how it communicates with the Pico. So on our Pico, we're going out of GPIO 0, and because it's an output going to our LED strip, there's no feedback in from the LED strip to the Pico. So we can get away with using 3.3 volts for our logic level, even though we're running the LED strips off of the 5 volts. And because there's no feedback from the LED strip to the Pico, we do not have to worry about damaging the Pico by running our LED strip on 5 volts. So I'm going to show you how to wire up your strip to your Pico. So this is the RGB strip from WaveShare, and you can see it has connecting pins on the bottom of it. So if you turn your board over, you'll see that the pins are labeled. So you can see the first pin is ground, the second is VCC, the third is the input or the data line, and then we have a fourth pin which is an extra ground. So I'm going to use black for ground, red for VCC, and yellow for my data line. So you can see I have the RGB module plugged into my breadboard. So the first pin is the ground wire that's going to pin 38 of the Pico. The red wire in the middle is going to pin 40 of the Pico, and the third pin is the yellow wire going to GPIO 0 on the Pico. And the fourth pin is not connected to anything. Now if you have this strip of 10 RGB LEDs, you'll notice that there is one end that has a connector with pins on it to plug into the breadboard. Unfortunately, this is the wrong end. So you'll notice between the RGB LEDs there's little cut lines. So this is where you can cut your strip, and you'll notice there's little arrows. So these little arrows are actually pointing to the right. So that means your data has to come in from the left hand side. And it's labeled here +5, D0, and ground. So when you wire up these strips, you need to use the connector at this end. And because it's a female connector, you'll have to run wires into each of those connecting holes. Please note that black is ground, red is 5 volts, and yellow is your data in. So you can see I've put some wires into the connector. So black goes to black, red goes to red, and yellow goes to yellow. So once again, the yellow lead goes over to GPIO 0. The red lead goes all the way over to pin 40, which is +5 volts from the USB connector. And the black wire is our ground, which goes to pin 38 on our Pico. So the book gives us some code to type in. A couple things I want to mention here before I type it into Thonny. You see where it says import RP2, and then underneath it says from RP2 import PIO state machine and ASM_PIO. You don't need both statements. You either import the entire library or you import parts of the library. So in my code, I'm going to leave off import RP2 and the code will work just fine. Now down here where it says number of LEDs, this is the number of LEDs in your strip. So if you have the white strip like I have, it's going to be 10 LEDs. If you have the wave share strip, it's going to be 8 LEDs. If you tell it that you only have 2 LEDs, all the other LEDs that come after it will be blank. The next thing I want to mention is this line here where it says at ASM. This is all one line, and you can see they ran out of room in the book, so they folded it over. So that has to go in as one entire line. You notice your main program is on a separate page that you need to type in as well. So I've gone ahead and typed the code into Thonny. You can see on line 3 I've just commented out the code that says import RP2 library because I'm going to import parts of it on line 4. On line 9 I have that entire line without it folding around on itself. So you can see on lines 9 through 20, this is the code that I want to run for my Programmable IO. And you can see I've defined it as WS2812. So on line 23, we're going to set up the state machine 0. And we're going to be using the code from WS2812, which is this code right here, which is not Python code. Please keep that in mind. And then we're going to activate the code. So the code's going to be active all the time, just waiting for us to send it information. So down here in our mainline code, what we're going to do is do an infinite loop. We're going to print blue, so that's going to show up down here in the shell. And what we're going to do is we're going to send a number out between 0 and 255. So what we're going to end up with is an LED that's going to be off and then turn on to full brightness. So we're going to do that for the blue, the red, the green, and then finally with all 3 colors on, we're going to have white. So rather than getting into the code right away, I'm just going to run it and show you the results. So you can see in the shell we've got the blue lights on, we've got the red lights on, we've got the green lights on, and then we have the white lights on. So there's the blue lights, the red lights, the green lights, and the white lights. So while they're white, I'm going to stop the code, and you'll notice all the LEDs are on. So what I'm going to do is I'm going to change the number of LEDs to 4. And now I'm going to rerun the code. And you notice now it's controlling just the bottom 4 LEDs. The top 4 LEDs are what are left over when I said I had 8 LEDs. So the book does a fairly good job of talking about the code, but it leaves a couple minor things out that I want to go over with you. So bringing up Thonny and looking at our code, I want to start with line 1 where it says import array. So an array is really a group of like data, and we usually use a variable to index it. So in our case, our array is going to hold the data for each of the LEDs. So in our case, it's either going to be 10 or 8 elements to our array. Now the interesting thing is that MicroPython doesn't natively support arrays, so that's why we have to import an array library. What is available to us in MicroPython is lists. And lists work pretty much the same way as an array, except in MicroPython, our array library will allow us to manipulate an entire array at a time. The next thing that I want to note is the assembler type language that we're using here. There's a few things that don't kind of jump out at us, which I want to mention. The first thing is this is running really fast. We're running a frequency, and if you group the zeros into groups of 3, you'll see that we're running at 8 megahertz. Now in the book it says that this code actually takes 10 clock cycles. So it's usually 1 clock cycle per line of code. But you'll note in here we don't actually have 10 lines of code. We actually have some jump instructions. And a jump instruction just tells you to go to another location. So a jump instruction usually takes more than 1 clock cycle. Now you'll notice in here we have a word called label, and it says bit loop. So if you come down here, you see a jump instruction. It says jump bit loop. So what that's doing is jumping up to this location, and because that's a label, it actually executes the next instruction, which is an out instruction. So keep in mind, I showed you earlier that a logic 0 and a logic 1 is determined by the duty cycle. So we have to be able to change the duty cycle within the frequency. So to do that, we can actually come in here and we can say, here we've got not X. So not X would be a 0. So a 0 is do 0. So we come down here to our label do 0 and we do a no op, which is no operation. It just takes a clock cycle. But you'll notice in here, if it is a logic 1, we're just going to come through here and we're going to jump to bit loop. So that's back up here. And we're going to continue to do this output. Now the other thing that's kind of interesting is we have some instructions on the side here. So this instruction is getting done at the same time as our out instruction. So this is our assembler language program, and basically what we're doing is we're sending information to it and it's sending out 1 bit at a time. So it's doing the work for us. So I'm not going to go into it in any great detail. But what is important to us is the MicroPython code. So what we're going to do is we're going to set up an array, and we're going to call it AR. So AR is an array, and basically it's going to create an element for each of our LEDs. So for each LED, we need to store the data and send it to our Programmable IO subroutine. So I want you to note that when it says print blue, it says for J in the range of 0 to 255. So each LED can have a certain brightness and a certain color. So the brightness is 0 to 255. So we're actually going to have our LEDs slowly turning on to full brightness. We have a second for statement. So we call this a nested for statement because it's within another for statement. And it says for I in the range of the number of LEDs. So if we have 8 LEDs, we're going to do this 8 times. What are we doing 8 times? We're going to store the data in J, which is the brightness of the LED, into our array element. So for each LED, we're storing the brightness, or the individual number 0 to 255. Now, the interesting thing to note about our Raspberry Pi Pico is that all the data that it uses is 32 bits. And because we have 3 LEDs in each RGB LED grouping, right, each one has to have its own number. So our numbers are 8 bits in length, and each LED has to have its own 8-bit number. So 3 times 8 is 24. So we need a 24-bit number. And our Raspberry Pi Pico stores all our numbers in 32s. So in here, when we're sending data to our state machine using the put method, we're sending the entire array, but we're cutting out 8 of those bits. So our 32 bits now becomes 24 bits. So then we're going to wait 10 milliseconds before we change it to the next brightness. Now, I've just said that we're going to be sending 24 bits. The first 8 bits are for the blue LED. The second 8 bits are for the red LED. And the third group of 8 bits are for the green LED. So the 8 bits for the red and the 8 bits for the green are all 0. So you notice in the next part of the code, we're going to print red. So we need to turn on the red LEDs. So we're going to do the same code that we used for the blue LEDs, but you'll notice down here our array is equal to J, and we have less than, and 8. So what we're actually doing here is shifting our data over by 8 bits. Then looking down at our third for statement loop, you'll notice we're going to shift the bits over by 16 bits. So this is for the green LEDs only. And then in the last grouping, where we want to put the white light on, we have to have the blue LED, the red LED, and the green LED on. So you'll notice our array element is equal to J shifted over by 16 bits plus J shifted over by 8 bits plus J all by itself. So J all by itself is blue, shifted over 8 bits is red, and shifted over another 8 bits is green. So we've come to the end of Get Started with MicroPython on the Raspberry Pi Pico. But before we go, I'd like to show you one last thing. So after completing Appendix C in the book, I just couldn't leave without creating a Night Rider pattern. Each of the NeoPixel lights are individually addressable, so each pixel can be red, green, or blue, or they can be individually on or off. So for this project, I'm going to use MicroPython's list feature. List really is like an array, but I'm not going to write to it. I'm not going to modify it. I'm just going to create it. So I've created 18 elements. Basically, it's going to be how I want the pixels to turn on across my entire NeoPixel display. So it's going to be 18 different elements long by 8 wide. If you have 10 NeoPixels on your string, the pattern's going to be 22 long by 10 wide. So once you've created your pattern, you have to be able to use it. So I'm going to use the same code that was used in Appendix C. The only difference is going to be in my MicroPython loop. You'll notice I now have in here a for statement for row. So for row in the range of 0 through 18. Then I have my brightness in the J range, and I'm going to go from 50 to 100 so it's not so blindingly bright. And then I go for I in the range of number of LEDs. The first thing I'm going to do is in my array I'm going to assign it the value of 0. Then I say if in my pattern row by column, if it's greater than 0, I'm going to assign J to my array element. Then I'm going to send it over to my Programmable IO port. So I do the same thing with the red, I do the same for the green, and then I do the same for the white. Please note for the 8-bit pattern, I'm going for row in the range of 0 to 18. When I'm using the 10 Neopixels, I go for row in the range of 0 to 22. These are the only differences between the two programs. So I'll put the two programs below in the notes underneath this video. I hope you enjoy them. So this really is the end of Get Started with MicroPython on the Raspberry Pi Pico. In the future I will do some additional videos on how to control higher voltages from your Pico, how to control servos and stepper motors, so please don't forget to subscribe, turn on notifications, and I hope to see you on my next video. Thank you for watching.